Okay, so back for statics. Determine the reaction at the wall, which is a fixed reaction. So we can look here at the wall and we can see that it's fixed. If I were to put a force on here like a diving board, it's not going to pin. If it was pinned and we put a force on it, it'd go doink, and it would just rotate open like a door. Because we have kind of that internal moment that's pushing back up, we don't have deflection until we move closer to the end of the beam. Okay, so draw our free body diagram, and we're going to start here, 8 kilonewtons. We have an applied moment of 25 kilonewton meters. We have an applied force of 5 kilonewtons. And at the wall, we could have X, Y, and applied moments. So I'm just going to call at the wall A. So I have AY, AX, moment at A. I have 2 meters, 2 meters, 2 meters. I have units, they're consistent, we've got kilonewtons and meters. So I have 3 equations. I'm going to sum forces in the x direction equals 0, and I get that AX equals 0. Again, I have to report AX equals 0 because if I were to change my loading and put a cable on here or a strut on here or change the way that this force is coming in, I would create X forces, and at this wall that's fixed, I would be able to resist that translation in the X direction. So now let's look at summing forces in the Y direction. Up is positive. In my world, I'm going to call it positive. You can call down positive if you want, it doesn't matter. And my rule over here, so I have AY, going to come across, plus 5 kilonewtons, going to come across, minus 8 kilonewtons, and I know that all of this has to equal 0 because we're in statics. So I have all of my forces on one side equals 0 on the other. So I can pull these over now, and I have AY equals negative 5 kilonewtons plus 8 kilonewtons. So AY equals 3 kilonewtons, and I assumed up, I got a positive value, so I know AY is pushing up at 3 kilonewtons. So again, you're going to have the magnitude, you're going to have the unit, and you're going to have direction. Up or down, if it's Y. Now, we need to calculate this moment that's applied here at the wall. So we have sum of the moments, and we're going to call it at A for now. We're going to sum the moments at A. If I start at the wall, I do have a resisting moment that's keeping this system from hinging down, and I have it right-hand rule positive, so I have moment of A. The X and Y components are acting at A. They are not a distance away. So we can ignore those, and now we're just going to move down the beam. Oh, I have 5 kilonewtons. If I were attached at the wall and I pushed up, I can see that I have positive rotation. So plus 5 kilonewtons times vertical or horizontal distance of 2 meters. As I come across, oh, I have an applied moment. And I want you to look at the units on the applied moment. It is already in kilonewton meters. It doesn't matter where I put this moment on my system, it's causing a counterclockwise rotation. So plus 25 kilonewton meters. Again, if I pin it at A, because that's my wall, and I rotate it around, it's going to be a positive rotation. Minus 8 kilonewtons times 2 meters plus 2 meters plus 2 meters, and all of this equals 0. Why is it negative? Because if I pin it at the wall and I push down, my clock handle wants to rotate like a clock, which is negative rotation. So I can move all of these to the right using algebra, and I have MA equals negative 10 kilonewton meters minus 25 kilonewton meters plus 2, 4, 6, 48 kilonewton meters. So my moment at A equals negative 35 kilonewton meters plus 48 kilonewton meters. So my moment at A, 35, 45 equals 13 kilonewton meters. I got a positive value, So my assumption of positive applied or positive reactive moment was correct. So that would be my solution to the moment. And how could I check my work? Well, I know that this is now 13. I know that this is 3. We could sum our moments. Let's just sum them about this point right there. Okay, let's check our work. Sum moments about that big giant point equals 0. Starting at the left. Clock handle, push down, positive rotation. So I have 13 kilonewton meters. Okay. Pinned here, force going up. Clockwise rotation is negative, minus 3 kilonewtons times 4 meters. That's my entire moment arm. Okay. Pinned here, push up, clockwise rotation. So I have negative minus 5 kilonewtons times 2 meters. Okay. I do have an applied moment here. It doesn't matter where I put that moment. If I'm twisting that clock handle, it's going to make a positive 25 kilonewton meter rotation. Even though I'm taking the moment at that point, it is still causing rotation. And then I have minus 8 kilonewtons times 2 meters. And all of this should equal 0. So I have 13 kilonewton meters minus 12 kilonewton meters minus 10 kilonewton meters plus 25 kilonewton meters plus 16 kilonewton meters. My units are working out, and minus 12 minus 10. Oh, this is a minus. Like, wait a minute, that is not equaling 0. What have I done with my math? Okay, what have I done? It should equal 0, and it's not. I forgot to bring the negative down. So I have 13 minus 12 minus 10 plus 25 minus 16. 0 equals 0. Check. So you should be able to check everything you do, and the reactions that you find should hold true.